Hello everyone. In continuation to our previous discussion of understanding what tensors are, let us look at performing certain basic tensor operations in this session. So before we begin with this particular coding exercise, I would like to draw an analogy in between a vector and one-dimensional tensor. All I am trying to explain here is a one-dimensional tensor is analogous to a vector and a two-dimensional tensor is analogous to a matrix. Any matrix operations or vector operations that we have done in the past are still applicable to these one-dimensional and two-dimensional tensors that we are going to create now. Okay, let us consider a simple vector dot product first. So let us create two different tensors u and v, that is vectors u and v. I'm trying to draw an analogy always. Okay, so torch dot tensor, and within the parentheses I provide a list of possible values for vector u or tensor u. And then I'm also creating another one-dimensional tensor by different values that are provided within the parentheses. Now u and v are two different one-dimensional tensors that we have created. You can verify that by referencing this particular attribute called endim. So endim is an attribute that provides us the number of dimensions associated with that particular tensor. All right. So now let's look at considering or representing these two different vectors u and v as column vectors. Essentially, these vectors are column vectors. So vector u is 1, 2 and 3. Vector v here is 1, 1 and 0. So now dot product of these two different vectors is nothing but u transpose v. The rows are now represented as columns and columns are represented as rows when you transpose a given vector. So u transpose, I am representing it as 1, 2 and 3. And now v, I am retaining it as is. So now I am trying to compute the product of every single element that's present within u transpose with its corresponding element that's present within vector v, right? So 1 is multiplied with 1 and then 2 is multiplied with 1 because we are always trying to multiply the corresponding elements in u transpose and v. That's how we do a dot product, right? So once we derive all of these products, you are just trying to sum them up. So 1 plus 2 plus 0 is going to result in a value of 3. So the dot product of two vectors u and v is a value of 3 now. So let's try to validate the same by using this particular function called dot. So within the parentheses, I am providing these two different tensors u and v and see if we get the same result or not. So we are now getting the same result. It resulted in a value of 3, which was exactly matching with the computation that we have done earlier. Okay. So it's not necessary that you always need to use one-dimensional tensors in performing these type of operations. So you can also use a scalar quantity like what I'm currently doing now. So I'm just trying to multiply this scalar value 2 to all the elements that are present in this particular vector u. So 1 is multiplied by 2 and then 2 is multiplied by 2 again and 3 is again multiplied by 2. So that results in a tensor of elements 2, 4 and 6. You also can add up particular scalar value to an existing tensor, which results in this particular output here. It's not necessary that you're always supposed to consider the one-dimensional tensors on as both these two different on left-hand side operand and right-hand side operand, right? You always can consider a scalar quantity as well while trying to do this arithmetic multiplication and addition. Okay, so you can do a element-wise addition as well. So the element-wise addition is given by this particular operator plus here. So every single element that's present within u is now added with its corresponding element in v. 1 plus 1 results in a value of 2. 2 plus 1 results in a value of 3. And 3 plus 0 again results in a value of 3. And 2, 3, 3 is a resultant tensor that we obtain here. So element-wise multiplication, which is nothing but the Hadamard product, is also possible. So now every single element in vector u is multiplied with vector v. So 1 multiplied by 1 is resulting in 1. 2 multiplied by 1 is resulting in 2. 3 multiplied by 0 is resulting in 0. So this is a Hadamard product. Hadamard product. Okay. Now let's compute similar operations by considering a two-dimensional matrix or two-dimensional tensor object to be more precise here. Okay. Torch.tensor. Let's create a two-dimensional tensor with values as 1, 2 and 1, 1. Okay. So now I'm creating another tensor object called T2. This time around, I'm just providing 1, 0 in row 1 and 0, 1 in row 2. My matrix T1 is 1, 2, 1, 1, and my matrix T2 here is going to be 1, 0 and 0, 1. So now element wise addition, that is T1 plus T2, is going to result in a output matrix of 1 plus 1 which results in 1, 2 plus 0 which results in 2, 1 plus 0 which results in 1 again, 1 plus 1 would result in 2 here. Okay, so T1 multiplied by T2 will be the Hadamard product, which is again element wise multiplication. Corresponding elements in T1 and T2 are multiplied. So 1 multiplied by 1, 2 multiplied by 0, 1 multiplied by 0, 1 multiplied by 1. It results in 1, 0, 0, 1. You can verify the same here by just doing T1 plus T2, which resulted in the same tensor as we have observed earlier. So T1 multiplied by T2 is going to be the Hadamard product, the element-wise multiplication that one can do. And in order to do matrix multiplication, it's a little different. So how do we do matrix multiplication in between T1 and T2? So 1, 2, 1, 1 is the matrix T1 and 1, 0, 0, 1 is a matrix T2. So now first we are going to consider row 1 from T1 and column 1 from T2. So we multiply the corresponding elements. So 1 multiplied by 1 plus 2 multiplied by 0. So we add the products here. And then for the second element here in the first row, in the resultant output matrix, you consider the first row and second column of T2. First row of T1 and second column of T2. So 1 multiplied by 0 plus 2 multiplied by 1, which are the product of corresponding elements here. And then for the second row, first element, you are going to consider the second row of T1 and first column of T2. So 1 multiplied by 1 plus 1 multiplied by 0. And the final element here is going to be the second row and the second column of T1 and T2 respectively. So 1 multiplied by 0 plus 1 multiplied by 1. So this here is going to be the result. So the result is 1, 2, 1 and 1. So 1, 2, 1, 1 is the result. So now let's look at implementing the same. So torch.mm, which is nothing but matrix multiplication in between T1 and T2, is going to result in an output matrix or output two-dimensional tensor as 1, 2, 1, 1, which is exactly matching with what we have computed a while ago. Okay, so we essentially have performed matrix additions, matrix multiplications, vector dot product. When we looked at the multiplication, we have specifically dealt with the Hadamard product as well as the regular matrix multiplication as well. Okay, so I would leave it as an exercise to you to explore more on additional operations that one can perform on two-dimensional tensor as well as three-dimensional tensor objects. If there are any questions, please revert back to us. We're always there to help you out. Okay, that's pretty much all I wanted to discuss with you in this session. Thanks for watching.